Hi, thank you for being here today. My name is Lin Lee, and I am excited to present our work on one prompt word is enough to boost adversarial robustness for pre-trained vision language models. In this work, we study the adversarial robustness of vision language models through the novel perspective of text prompt. Our work aims to demonstrate the potential of defending vision language models against visual adversarial examples via text prompt tuning. Throughout this presentation, I will walk you through the motivation behind our research, our methodology, key findings, and the implications of our results. Let's begin by understanding the context and significance of this study in the broader field of adversarial machine learning. It is well known that deep neural networks are vulnerable to adversarial examples. An adversarial example refers to a clean image with added noise that is imperceptible to humans but designed to fool the model, as illustrated in the top figure. This poses a significant security risk for real-world applications relying on these models. Recently, it has been demonstrated that state-of-the-art vision language models are also highly susceptible to adversarial examples. The bottom figure shows an image captioning model being misled by an adversarial example to generate a link to a malicious website. This work investigates the adversarial robustness of vision language models from the perspective of text prompts. This novel approach is chosen for two reasons. First, text prompts are unique to vision language models compared to vision models like CNNs and VITs. Second, the impact of text prompts on adversarial robustness has been less explored. Specifically, this research addresses two questions. How do text prompts affect adversarial attacks and defenses? Can tuning text prompts improve the adversarial robustness of vision language models? In this work, we use CLIP as a representative vision language model. CLIP consists of two encoders, one for text and one for images. During pre-training, it learns to align the visual and textual features of paired images and text by optimizing the weights of both encoders. In the inference stage, CLIP constructs text prompts for all classes using their label text and predicts the class whose textual feature best aligns with the visual feature of the queried image. Text prompt refers to the input provided to the text encoder. For image classification, CLIP constructs prompts for each class using a template such as a photo of a class. This can be generalized as shown in equation 2. In this study, we assume that the class is determined by the dataset while the context can be adjusted. A common approach to generate adversarial examples for a vision language model involves finding a perturbation for the input that maximizes the cosine dissimilarity between the image feature and the text feature corresponding to the ground truth class prompt, as shown in the equation 3. An essential design choice in adversarial attacks is the selection of the prompt, referred to as the attack prompt. Notably, the attack prompt can differ from the text prompt used for inference, referred to as the inference prompt. To assess the impact of attack and inference prompts on adversarial robustness, we conduct experiments where we freeze the model weights and evaluate robustness under 6 distinct prompts for attack and inference scenarios separately. The accompanying figure illustrates the robustness of the pre-trained CLIP model across various prompts used for inference in rows and adversarial attack in columns. Within each row, the minimum robustness is denoted by the absolute value, while the remaining values indicate the deviation from this minimum. Our findings reveal several key observations. Firstly, robustness fluctuates as different attack prompts are employed against the same inferencer prompt. Secondly, the lowest robustness, indicating the strongest attack in each row, consistently occurs when the attack and inference prompts align. Lastly, robustness levels within each row exhibit variability based on the inference prompt utilized. Inspired by the third observation, we propose a novel method called adversarial prompt tuning, aimed at enhancing the model's resilience to adversarial attacks by refining the inference prompts. Our method begins by parameterizing the text prompts, enabling optimization through learning-based techniques. This process involves formulating the context of a class using a sequence of vectors within the word embedding space, each vector defined by 512 parameters. These vectors are optimized towards minimizing the adversarial loss, a process akin to traditional adversarial training as depicted in equation 5. To assess the efficacy of our approach, we conduct extensive evaluations across 11 datasets, including ImageNet. Our method presents 3 compelling advantages. Firstly, our method showcases exceptional parameter efficiency. With the utilization of a solitary context vector comprising a mere 512 parameters, we observe a substantial average increase of 13% in accuracy and an impressive 8.5% enhancement in robustness. Secondly, it demonstrates remarkable data efficiency. Through the utilization of a single shot, one image per class, our method yields notable performance improvements, with accuracy seeing a commendable increase of 6.1% and adversarial robustness experiencing a discernible rise of 3.0%. Lastly, our method underscores profound effectiveness. Upon employing the entire training set, we witness a remarkable surge in performance metrics. Specifically, accuracy experiences an outstanding boost of 26.4%, while adversarial robustness demonstrates a significant increase of 16.7%. Furthermore, our method also demonstrates remarkable out-of-distribution and zero-shot generalization abilities. In closing, I want to emphasize the key takeaways from our work. Firstly, we've observed the nuanced sensitivity of adversarial attack strength to the choice of attack prompt. Secondly, our findings highlight that potent adversarial examples often emerge when the attack prompt aligns with the inference prompt, emphasizing the criticality of attackers having access to the latter. Thirdly, we've identified the significant impact of inference prompts on the adversarial robustness of CLIP. Lastly, our study underscores the potential of text prompting to substantially enhance adversarial robustness. Overall, our work paves a new way for enhancing adversarial robustness for vision language models through text prompting. Thank you for your attention, and I look forward to any questions or discussions that may arise.